Alright, so Billy Bob's going to let off a bit of a steam. He's going to kick a ball really hard. That's going to provide a force, and the ball will launch at 30 degrees and travel at 40 meters per second. It'll reach the zenith and then it'll land. And this is all occurring in an acceleration of 9.8 meters per second. Now if we look at the side view, the ball goes up and then it goes down. And because there is a force acting on that plane, we can use the following equations that have acceleration. Now if we look at the top view, the ball just appears to be travelling in a straight line because there are no forces acting in that plane. So there is no changing acceleration, so the velocity is constant. So velocity is equal to distance over time. Now the side view is referred to as the vertical plane, and the top view is going to be referred to as the horizontal plane. The common feature between the vertical and horizontal components is actually time, and that's a non-vector quantity. So that is the wild card that converts two sets of one-dimensional motion into two-dimensional motion, as I'll demonstrate in the examples below. Now we're going to break down Billy Bob's velocity of the ball that's launched into its separate components. So we've got vertical velocity and horizontal velocity. Now using trigonometry, the vertical velocity is opposite the 30 degrees, so it's using the sine function, and the horizontal velocity is adjacent, so we're using the cos function. Now if we rearrange those equations, we can actually solve the individual vertical and horizontal components of motion. Now to work out the zenith, or the maximum height, we're going to assume that the vertical velocity at its peak is equal to 0, and its initial vertical velocity was actually equal to 20 as we previously calculated. So we're just going to use v squared equals v naught squared equals 2as, substitute our values in, and we'll calculate our height. Now to calculate the time of flight, or TOF I like to use for short, we're going to calculate the time to the zenith and then times it by 2, because the time it takes to go up is equal to the time equal to go down. So velocity equals initial velocity over 8t, rearrange that, substitute our values, and of course we work out a time of 2.04 seconds. Times it by 2 and we get 4.08 seconds. Now we have the total time of flight, we can actually calculate the range. So as I alluded to before, velocity equals distance over time, just rearrange that to distance equals velocity times times, substitute the velocity, the horizontal velocity now, and time can go in, and we work out the range to be 141 meters. Alright, so now we're going to do it if Billy Bob was actually kicking the ball from a height. And now the height we're going to choose is a 2 meter height. So he kicks the ball again. However, it's actually going to be travelling further, as indicated by the dotted line here. Now we're going to break this into two components. So we've got the zenith indicated there. So the first half we're going to call part 1, the second half we call part 2. So the time of flight we already calculated for part 1, none of that's going to be affected. However, we need to recalculate for parts or section 2. The new displacement, or the maximum height, is going to be the previous height plus the 2 meters of the box. So displacement equals v naught t plus a half 8t squared. We're now using the new height. The initial velocity as it falls from the top is equal to 0, so that cancels out. rearrange the equation to work out the time, substituting our values now and calculating for time. Please note the answer is bigger than the previous section, so that you should be expecting that. Now the time of flight is going to be the first and second stages added together. Now we've got the new time, we can calculate the range by timesing it by the horizontal velocity. Before proceeding to work out the final velocity, we need to calculate the final vertical velocity. To do this, we're going to substitute in our new height of 22.04 meters. Now, as it's falling, the initial velocity was equal to 0, so that cancels out. Substitute, rearrange, usual protocol. To calculate the final velocity in terms of magnitude and angle, first we're going to draw a vector diagram of the velocities that we have, and the sum will be the hypotenuse of this triangle. And we'll use simple Pythagoras to actually calculate the total velocity, which includes the vertical and horizontal components. Now to work out the angle it's going to collide with the ground, we work out the top angle, and that's going to be alternate angles. So we've only got the adjacent and opposite side, so we'll use the tan function, substitute our values and actually work out the angle. Very important to actually put in the reference for the angle, and also back in the original diagram stating it was alternate angles.